What is Lagrange? Lagrange was a mathematician, I think he was French, and he came up with another way of looking at classical mechanics. So he didn't come up with a new mechanics, he just figured out another way of doing it. So let's start at the beginning. What was the guy's name? His name was Joseph Louis Lagrange. And he lived between 1736 and 1813. And he developed a new look at classical mechanics. So I'm just going to call it a new look at classical mechanics. So he didn't come up with mechanics that was different from what Newton was giving us. He just came up with a new way of looking at it, okay? And he called it Lagrangian mechanics. L. And he defined it as T minus U, or in a lot of textbooks, it's also written as T minus V. If I do U's or V's in this class, they are the same thing. In the textbook, I have used V's everywhere, but they're the same as U's. Okay, so it's always defined as T minus V. But remember, these are all energies, where T is what kind of energy? Kinetic. And what is U? Potential. And what is V? Potential energy. They're all the same. Okay, so why did he think that that was something worth pursuing? Well, the reason why he thought this was worth pursuing was we did Newton's laws, right? So one of the big issues with Newtonian mechanics was that when we deal with Newtonian mechanics and when we had two masses, how many equations did we need? At least 4, right? Now, if I additionally have another coordinate, so we live in a 3D space, for 2 particles, how many equations would we need? 6. Now, what if we had 3 particles? 9, right? Now, what if we had 4 particles? What if we had 50 particles? What if we had n particles? You need 3 times n equations to be worried about. So imagine if you have 1 mole of gas. How many particles are there in 1 mole of gas? Avogadro's number, right? Which is 6 point something times 10 to the 23rd times 3. Now, how do you keep track of all of that?
Well, and that times.
It will be that times 3, right? So there were disadvantages of using Newtonian mechanics. The other big disadvantage is, do you remember we said that Newtonian mechanics or Newton's force equations only exist in what kind of a frame? An inertial frame, which means acceleration equals 0 for that frame of reference. Now, what about all the other frames that might be accelerating? You can't deal with them, right? So someone had to come up with something different that could deal with all of those situations. So Lagrange came up with this formalization where, if you notice very carefully, oh, and another disadvantage, sorry, before I continue, another big disadvantage of Newtonian mechanics was that it only deals with vectors, right? So we have to worry about x, y, plus, minus every single time things change. But if you look at Lagrange, what does it actually tell you? It is only T minus V. T is kinetic, V is potential energy. Are energy scalars or vectors? scalars. So they're just numbers you're dealing with. Suddenly your life becomes so much more simpler, right? Because now you are just dealing with energies which are scalars. Two, you are not worried about what kind of a vector is this, because energies are not vectors. So you're not worried about pluses and minuses necessarily, right? Plus, energies don't care. They're just energies at that spot. So now let's write all of this down. Ready? So the first issue was the second law or force equation must be applied one to each and every particle, right, in our situation. And number two, each and every axis under consideration, right? So suddenly you have, for two particles, 6 equations or 6 force equations. For 10 particles, how many equations of motion? And each of them will have their own x and y and z, pluses and minuses, depending on what they're doing. Now add a bent coordinate on top of it. Add freely moving random particles. How do you keep track of all of that? Well, you don't. Yeah, exactly. The other issue is, with Newtonian mechanics, it applies only to inertial frames, right? Which means acceleration equals 0. Which means if you're looking at an apple falling on the earth from Mars, looking down, they won't work. Number 3, the Newton's second law, I should call it Newton's second law, is a law of vectors, which work really well when you work with vectors and work with Cartesian coordinates. But it becomes really messy when you try to change coordinates. So it gets messy when we try to change coordinate systems. So next we can talk about solutions. Lagrange defined his Lagrangian as T minus, I'm going to stick with V. Okay. How should we think about this? We should actually think about it like this. R dot R, where T is a function of R dot and V is a function of R. This is kinetic energy. This is potential energy. And think of these as that. What is R? Position vector. It will incorporate X, Y, Z in it. And what is R dot? Velocity vector, right? It is the derivative of that, because T is defined as we define it as 1/2 mv squared, right? But V can be written as x dot, y dot, z dot, jk, and V squared is x dot squared plus y dot squared plus z dot squared. Be very careful. I've seen this mistake when students sometimes make they'll say, oh, 1/2 mv squared, which is equals to 1/2 m x plus y plus z squared. That's not true. The other thing is V can be many multiple different things. V is just potential energy, and we will talk about potential energies and its forms. So here's the cool part. Kinetic energy doesn't change no matter what kind of a system you have, but potential energy does. Potential energy depends on the system you have. It could be many different things. And when I show you, actually, I could talk about, no, actually, hold on to that thought. We'll talk about it. We also know from Newtonian mechanics, F equals dp over dt. And we also wrote F as minus delta U, where delta was what? Partial over partial x. Remember that? So then F is actually a d over dx of U with a minus sign.